Thanks a lot for the invitation. It's great to be here. So I'm going to talk about over-parameterization in neural networks, and all of this is joint work with a colleague at UC Riverside, also in Southern California. So I'll motivate this from a more theory perspective. Obviously, deep learning doesn't require motivation at this point. There are a lot of success stories, obviously, in neural networks. They've been extremely successful at things like speech, text, images, and so on. So there's a lot of success here. But at the same time, there's obviously also a lot of hype. Actually, as a PhD student at Stanford, I started in 2009. Every year by the computer science faculty, we were promised that next year we will have self-driving cars. Radiologists would kind of be extinct, but it's been 10 years, right? So those things haven't happened yet. And part of the reason for that is sometimes these heuristics work very well, but at the same time, sometimes they fail. And in my opinion, this kind of motivates a more theoretical understanding of what is happening. So there is really a need for more principled understanding of things that are happening. And this is particularly important if we're going to use these techniques in things that have human-facing applications, right? Whether it's, again, stuff like self-driving cars or medical diagnostics, things of that sort. And so the kind of theoretical challenges that, at least at a high level, I see and the community sees is there's kind of three challenges. The first one has to do with optimization, right? These neural network training problems are extremely non-convex, non-linear, and it's not completely clear why do you converge to a global optima, right? The second question is more on the generalization side, which is, let's say they even converge to a global optima. Why is that any good, right? Why is the neural network that you train actually generalized to yet unseen test data, right? How is its prediction capabilities? And of course, the hope here is that if you develop these kinds of understanding, maybe you can even impact system designs, architectures, and so on, right? I'll mostly talk about the first two in some sense here today. So I'll focus on a very particular aspect, which is understanding this role of over-parametrization. And so here, the kind of mysterious phenomena is that neural network models are often trained, and I'll show some experiments in a second, in a regime where the number of parameters in the model are much larger than the size of the training data, right? And classical thinking in statistical learning says that if this happens, you usually expect to overfit. But what really happens is that you just do things just right? And so we want to explain why this happens and some questions surrounding this. So let me show some experiments. The first one, set of experiments is actually stolen from Ben Recht, a former mentor. So here, the kind of experiments Ben and his co-authors did, what they showed is that for a variety of different popular neural network architectures, if you remove all the bells and whistles and just run SGD, what you observe is that you always hit global optima. But the surprising aspect of this is that the number of parameters over the size of the training data, so that's this ratio P over N here. So this is always kind of bigger than 1. And in fact, the more popular architectures seem to be even higher, much higher than 1. So the first question here, again, is optimization. Why is it that you can hit 0 training error? Perhaps this one is not that surprising because, you have an over-parameterized model. There's many global optima. And so maybe it's not surprising that there's a huge null space, so you find a global optima. But of course, it's not that clear because the problem is nonlinear, non-convex. There's all those issues. The second, and this one is arguably more surprising, is that not only do you find a global optima, you find one that is good. As you can see, the test error keeps going down, even though you keep over-parameterizing more and more. Okay, so that's kind of the first surprising experiment. This is a couple of years old, so maybe not that surprising at this point. But the second one, the variation of this was also included in that paper, is like if you start adding corruption, neural networks can still be trained to achieve zero training error. So here, the corruption model I'm going to focus on is like you basically take a fraction of your labels and you change it from the true labels to some other label in the classes that you have. So it's like a classification problem. Given the label that you have, so here you take 0, and instead of giving it the true label in your training data, you actually give it 8. Okay, so you corrupt a fraction of the labels, and then you just train your neural network, right? And so this is like a very simple ZNet type model, but it's slightly more over-parameterized. This is after like 200 epochs. So what you observe is I'm showing 3 different things in here. So on the x-axis is the fraction of the corruption I add. So I corrupt randomly a fraction versus accuracy, right? And what you observe is that, well, the train accuracy keeps being perfect. It's 100, meaning that you still perfectly fit the training data. But of course, so meaning that the neural network is definitely rich enough to really overfit to the training data. But at the same time, you see that obviously this is overfitting. The test data performs poorer and poorer. And another thing I want to depict here is like, if you measure train accuracy with respect to the true labels, not the corrupted ones that we put in, obviously the performance will be bad, right? So this just says that, you know, it's not a matter of these models not being rich enough. They're definitely rich enough to fit any data set, including random corruptions, even at 100% corruption, which is just random noise. Okay, so that's the second. So they have the capability to overfit, but somehow they don't on real data. This one, I think, is more surprising, which is, so let's repeat the same experiment, right? But let's stop the algorithm early, okay? So we don't let it run for 200 epochs, but we stop somewhere in the middle. So this is with early stopping. Now something interesting happens. So the train accuracy now goes down. So now you're not actually fitting to the train data. And in fact, this data is corrupted, right? Like on the x-axis, remember where the fraction of corruption, you actually don't want to fit to the train data. But so after early stopping, you can see that actually if you look at the test error, it remains consistently high, even for relatively high corruption levels, up to even 50%. So what is more interesting, if you actually look at the kind of a red curve, which is train accuracy with respect to the true labels, you see even up to 30%, 40% corruption is still at 100%, meaning that the algorithm actually corrected the wrong labels and assigned it the correct ones. Okay, so meaning like these over-parameterized models have like this inherent robustness to them, which is quite surprising, right? And so these are kind of the things we want to try to begin to explain. So this is just a different view of the same effect. Here I'm drawing accuracy as a function of the number of epochs for when you have 50% corruption on your labels. And you can see, so you can see that definitely at some point you start overfitting, right? The train accuracy goes high, but the test accuracy starts dropping. And so these are the overfit regime. But if you stop before that, then you don't overfit. So these are just the histograms. So here is basically the cross entropy loss of the individual data points. I'm drawing the histograms. And you can see at the beginning, they're kind of very well separated, meaning like, you know, so this is for the corrupted labels versus the clean portion. You can see they're pretty much well separated. So this means that you are learning something useful. Here, they're kind of together mixed. So here, you don't learn anything useful in this model, right? So that's the experiment. And so in this talk, I'm going to try to explain some of these things. So I'll talk about 3 benefits that this over-parameterization buys you. The first one is that it actually does make optimization a bit easier. And then I'll talk about robustness and maybe a little bit about generalization at the very end. OK, so let's see how it makes optimization maybe potentially easier. So I'll focus on just a single hidden layer neural network, so it's not deep. Some variation of this argument can work for deep, but it's not that interesting. I'll talk about that later. So, so here, the notation is that the input is x, is in little d dimensions. And then you map it to hidden layers, you pass it for nonlinearity, and then you do a weighted combination. And I'm assuming there are k hidden nodes. So d is the input, k is the number of hidden nodes, and little n is going to be the size of the training data. OK, so I'll focus on kind of regression tasks. So let's say you have a data set against training data set of size n. You fit like a least squares model on this data set. And so you would want to run gradient descent. What we're going to do is just fix the output layer and just run gradient descent on W. You could run it on both, but it just simplifies the presentation a little bit. So we set V either at random or somehow something that is well balanced, meaning like there is half is +1, half is -1, a model like this. So in some sense, it just needs to be balanced. And then we run gradient descent on the input weights, right? So you run gradient descent over W. And so here is our first result about this. This is for smooth activations. So the assumptions are that the first and second derivative of the activation function is bounded. So if you're wondering what kind of activation function fits that profile, think of like soft plus, like log 1 plus e to the x, which I've drawn there. So that kind of activation. So the other assumption is that the network needs to be over-parameterized in the sense that the square of the number of parameters, so k, remember, is hidden nodes. So here, remember, k is hidden nodes, d is the input. So k times d is the total number of parameters that we really have. So as long as the square root of the number of parameters is bigger than the size of the training data n, by a constant that depends on data, and I'll explain what that constant is, then, so that's the second assumption. And the last one is that you have to initialize at random. Okay, so under these assumptions, a few nice things happen. First is that with high probability, you actually achieve zero training error, right? So you converge at a geometric rate to zero training error. That's one. The second kind of nice property, which is actually going to be key in the second part of the talk, is that you remain sufficiently close to your initialization. Not too close, but it's still relative error order 1. So that's the second result here. So this result is for these smooth activations. You might be wondering, OK, so what can you show for ReLU? We can, let me actually talk about this quantity kappa before I talk about ReLU activations. So this kappa, you can think of it as kind of like a condition number of the data in some sense. So it kind of measures the diversity of your input data. And to see why this should play a role, so imagine the following scenario where you have two different images. The same image, but you assign it to two different labels to it, right? So you have cat, but the labels are one is cat, one is dog. Obviously, in this scenario, you cannot overfit, right? And the reason for this is that your input data is kind of the same. It's not diverse enough, right? When there's different labels associated to it. So to capture this diversity, we have this quantity that you can think of as a condition number. Essentially, what this is kind of a normalized spectral norm. The factors behind it is just the appropriate normalization for this data matrix. Over like this quantity lambda of x. This lambda of x is kind of a minimum eigenvalue, but it's essentially the minimum eigenvalue that comes out of the expected value of the Jacobian of the mapping at initialization. There's also another interpretation, which is like if you let the number of hidden nodes go to infinity, that's kind of like the covariance of your neural network in some sense. And so this is the minimum eigenvalue of that. And let me just mention that this quantity actually does scale like a constant, at least when the data is very diverse. So in particular, using some Hermite expansion stuff, what you can do is you can relate this neural network covariance and the minimum eigenvalue to that of, for any activation, to that of quadratic activations. And what this would allow you to do is basically for data points that are uniform on the unit sphere, you can actually literally show that this quantity scales like a constant with high probability. So in general, it's data dependent. If you are maximally diverse, uniform on the unit sphere, it scales like a constant. Okay, so you can really think of it as a sort of condition number of your data. So for ReLU, again, same setup, but now the activation is ReLU. Exactly the same setup. Now the only thing that changes is like kind of the required amount of over-parametrization here is a little bit larger. So you need more over-parametrization, but all the conclusion statements is exactly the same. So all of this also works if instead of gradient descent, you were to use SGD. So nothing really changes under the same set of assumptions. The only difference is that obviously because you're updating one at a time, n iterations of SGD have to correspond to one full gradient pass. So the convergence rate gets divided by n. Before it was d1 minus d over n, now it's 1 minus d over n squared. So n passes of SGD does correspond to like a full gradient pass, which is normally what you would expect, right? So that's the result for SGD. Okay, so let me give you a brief proof sketch of how this proof works. So before I actually talk about like the neural network example, let's just look at a very simple linear model, right? Over-parameterized linear model. So this is very simple. So here you just have the number of basically data points, again, is less than the number of parameters. So in this case, it's really very simple to show that gradient descent on something like this, if the step size is small enough, a few nice things happen, right? First is that obviously if you run gradient descent with a very small step size, you converge to global optima, right? That's very easy to show. Second is that not only do you converge to global optima, the global optima that you converge to is the closest one to your initialization, right? Out of all the members of a null space, you pick one that is closest to your initialization. And the third interesting aspect is that not only that, the total gradient path is controlled up to condition number issues. So meaning that you essentially follow a very direct path from your initialization to this closest global optima, modulo conditioning of the problem, right? So that those are what we know from just these squares. And so the rough idea is that you can try to mimic this argument to some extent, but in a time-dependent fashion. And so here, if you have like now a nonlinear least squares problem, so instead of fitting a linear model, you fit some nonlinear mapping f of theta. Theta is in RP, is the number of parameters, and the output is n-dimensional. So this doesn't even have to be neural networks. So if you fit a model like this and you run gradient descent, here the gradient takes the form of like Jacobian transform times the residual. So if you don't remember what the Jacobian is, it's basically here it would be a n by p matrix, right, where the rows are gradient for the ith output of the function. So that's what it is. And so essentially the idea is that for a given iteration, you can think of this kind of the same as the linear model, except that this time-dependent j of theta replaces your kind of data matrix X. So that's roughly the intuition. So you cannot exactly show what we discussed before, but what you can show here is that if on kind of a sufficiently large radius, some nice things happen. So first of all, Jacobian at initialization is sufficiently bounded away from 0 in terms of minimum eigenvalue. The Jacobian is bounded over this kind of radius, and it's kind of behaves smoothly. Then, first of all, and this is the last condition, which is residual needs to be sufficiently small, which you can show for random initialization typically. Then, if you pick a sufficiently small step size, you get all of the nice properties that you kind of saw for least squares. You get global geometric convergence. You don't exactly get convergence to the closest global optima, but an approximately close one, in the sense that if among all, let's say the closest global optima is like theta star, so your iterates always are close to the distance between theta star and theta 0 by a factor that is kind of, again, like a condition number of the problem. So you converge to an approximately close global optima among all of the possible global optima. And you can also show that, in fact, the total gradient path is also well controlled, modulo conditioning, so that you are actually literally following a direct path from your initialization to this approximately close global optima. And here the key idea is that, obviously the problem we were looking at before is linear. So here you keep track of this sort of Lyapunov function, which is the sum of the residual plus the total gradient path. So that's the idea. So this is what allows you to go from linear to this nonlinear model. So let me also explain roughly how this proof works for the SGD setup. So if you actually use stochastic gradients instead of full gradient. Okay, in this case, the real challenge, obviously, if you want to go from SGD to gradient descent to SGD, usually what you have to do is essentially take expectations and control some sort of variances, and things work out. But here, because the problem is non-convex, there is this added challenge of you have to make sure that the iterates remain in this neighborhood, in this local neighborhood containing the initialization and this close global optima. So you have to make sure that you don't escape from this neighborhood. And so this kind of adds a new level of challenge in this problem. And so the first idea one might have is, okay, is like, say, let's try to kind of come up with a super martingale, right, to show that, the probability of leaving this local neighborhood is very small. Like by looking at the stopping time of the exit, the probability of exit, say if that is small, then you kind of stay in this neighborhood with high probability across all of your iterations. And so one can think, okay, maybe I just need to show my Karen parameter to initialization. This is what I want to control. Maybe that is a super martingale, and then I'm done, right? It turns out that that's not true. And there's kind of an approach that was used in other non-convex problems, much simpler ones that appear in phase retrieval by Vershinin and his student. But this approach won't work here because, in fact, this is not a super martingale. I mentioned that we have this Lyapunov function. You might think, okay, maybe you can show that this Lyapunov function, is like a super martingale. This also doesn't work. What we ended up showing is that what you can do is you can cover this radius. So you have a covering of this radius, and you try to show the average of the distances to this cover is a super martingale. So essentially, you cover this ball with a bunch of points, and you show that the sum of the distances to this cover is a super martingale. And from that, you extract that you don't move far away. And so in case this is not clear, the mental picture I have in mind of this is something like this. So if you pin something down from different points in the cover, so this means that you cannot move too much, right? So that's the basic idea. Okay, so let me just explain how this translates in the context of this one hidden layer neural network. Again, here, the parameters is like k by d dimensional. It's like the weights. The Jacobian here will look something like this. It's kind of like the Khatri raw product between your data and other points. And so the key techniques, the key idea is to just go through those list of assumptions and try to show that those 4 assumptions actually hold for this problem. And the way you do that, I'm not going to go through that, but there's kind of two key ideas that allow you to do that. The first one is by noticing that this Jacobian has a very particular form, so that if you look at this Jacobian times Jacobian transpose, it has a very nice Hadamard structure. It's like the Hadamard of these two matrices. And then you can apply this classical result by Schur, which says minimum eigenvalue of the Hadamard product is at least, the more classic one is you show minimum eigenvalue of one times minimum eigenvalue of the other. Here is key that it's actually you can replace one of those minimum eigenvalues with the minimum entries on the diagonal. It actually turns out to be very key in this problem. And the second one is that obviously because at initialization you start from a random Gaussian thing, you have to be a little bit careful in terms of analyzing basically the spectrum of this Jacobian matrix at the random initialization. So there are some simple ideas from random matrix theory that goes into here. Okay, so that's roughly the idea. I just want to mention that this idea of over-parameterized learning, before I actually move to the second part, this actually works beyond just neural networks. This kind of theory actually can apply other places. So in particular, like remember yesterday morning, Irene gave this nice talk about Bure-Montero approaches and so on. She was discussing lower bounds, but you can actually use this to show upper bounds in other regimes. So in particular, if you have a matrix factorization model, was looked at in that talk, now if you assume any labels, but you assume just the matrices involved are random Gaussian, then you can show that essentially gradient descent from random initialization converges to the global optima as soon as the number of data points is less than the dimension of the model you're trying to fit. So here you're trying to fit a low rank model of dimension d by r. So it's a d by d matrix, but it's low rank, so the number of parameters is d times r. So as long as the number of points that you're fitting n is less than d times r, and this is exactly less than or equal to, then you can show global convergence from a random initialization. And so the reason this is kind of nice is, like as you saw in that talk, typical Bure-Montero results is that if the rank is bigger than square root of n, things work out. Here we're saying that if the rank is bigger than n over d, things work out. So in particular, if you assume the labels come from a low rank matrix, actually, so there is actually a low rank matrix corresponding to your data. Let's say, which has some rank r0. So typically, the number of data points you would have is d times r0. The classical Bure-Montero result would tell you that r is bigger than square root d times r0, whereas this kind of result would tell you actually the rank only needs to be bigger than the true rank by a constant factor, right? So essentially, this is not, this provides like a more example of the positive direction of the Bure-Montero, that the rank doesn't have to always be bigger than square root of n, it can be much, much smaller. And this is the good thing about this is even though you assume the measurements are kind of random, AIs are random, the labels could be arbitrary, right? So there is no condition on the labels. They don't even have to come from a low rank model. Okay, let me just discuss some interesting previous work and see how our results kind of compare. So we actually looked at this problem a few years ago with quadratic activations, which of course was not practical, but maybe it was a starting point. So more recently, people have looked at this. So here are the results for smooth activations, which is if the number of, and the results is basically if the width of the network, k, is bigger than n to the 4, then you get global convergence from a random initialization. What we're saying here is that if the number of parameters is bigger than n squared, you get global convergence. So we go from width to really number of parameters, which is, I think, the right quantity. And I'll discuss why this is particularly important in this setting a bit later. So same for ReLU. We also go from assuming, again, the number of hidden nodes is large to some parameter-dependent quantity. So previous results are n to the 6. We go to n to the 4 divided by d to the 3. There's also another different set of literature that uses a different kind of assumption on your input data. This has to do with separation of the input data. Those kind of results require kind of at least from what I read of the paper, but I can't tell exactly, require n to the 25 over this separation quantity to the power 8. We improve that to like n to the 12. Okay, so this, let me just try to explain a little bit why it's important to go from width to parameters. Because essentially when you assume the network is very wide, the way this argument works is that you essentially you can show that the value of the hidden nodes as you iterate do not change much, right? And this was, I think, demonstrated by this paper by Chizad and Bach, and I assume he might actually talk about this tomorrow. So basically, so this is what's called the lazy training. So if you just assume the network is wide, you might be in this lazy training regime. And so we're beginning to move away from this lazy regime. And the other benefit our result has is that actually you get much faster convergence rate. Actually, it's by a factor n faster. So I should say that our results, we have not sat down and worked it out for deep networks. Some of these results have been worked out for deep networks. And the kind of assumptions here is that if all of the hidden units are sufficiently large, number of hidden units, all the layers, then this works. Our result we can do something like this if you assume the number of parameters of the last layer is large. So it's a little bit less restrictive than these results, but maybe still not that interesting because you still have to assume the number of parameters of the last layer is larger than the size of the training data, whereas like total number of parameters, right? So it's still kind of restrictive, so we didn't really bother. Another kind of class of interesting results is like it's a more asymptotic analysis, which looks at kind of like if you start with very small initialization and you let all the number of hidden units go to infinity, you can kind of get more precise results by kind of mean field analysis. And again, I assume this is what Francis Bach is going to talk about tomorrow. So the difference here being that these results are more asymptotic in nature, whereas we're kind of for fixed dimensions. And of course, in a broader literature of theory of neural networks, there's so many results that there's just not enough time to go through all of them. So before I end kind of this portion of the talk and move to the robustness, let me briefly mention that the one reason that going beyond width is important is like if you just pick W completely random and train for V, the output layer, things you can fit everything because it's just a linear problem as soon as k is bigger than n, right? So this is why it's particularly important to go beyond width because you just train the last layer, you already can get k bigger than n. You don't need k bigger than n to the 6, right? And so it's really important to bring in the number of parameters versus just width. And I should still say that there is a huge gap between what we can prove and what seems to hold in practice. Remember, we said, and this is like shows my compressed sensing pedigree. It's a mandatory phase transition plot, right? So if you look at kind of, if you run this for random data and random labels, you start to see when can you achieve this global optimality is as soon as KD is number of parameters is bigger than n. We proved n squared, remember? So there's still a huge gap. These phase transition plots at least show for random data there's still a huge gap. Really parameters versus number of data points seems to be the right quantity, at least based on these experiments. And again, it also holds across the board. Whether you use something smooth, whether you use ReLU, it still seems to hold. So okay, so let me, in the remaining time, let me briefly talk about kind of the other set of results which had to do with this robustness, and this will be actually quick. So I just want to explain this a little bit of why does this happen. So here, I'm going to make a little bit of a more crazy assumptions, but we're going to verify it in some sense on data. I'm going to assume that the data is clustered in some way in this data model. So I assume there are L clusters. Each class can have multiple clusters. So there are L clusters, K classes. And the other strange assumption I'm going to put here is that the labels are in R1 instead of usually you would put them in RK, but it just makes analysis simpler. And I'm just going to assume the labels are delta separated. So in general, it would be like square root 2 separated if you assign 0, 1 labels. And then we're going to remember we want to corrupt the data. So we're going to pick row fraction of the data points and just corrupt them by assigning it any other label. And then run gradient descent. So here is what we can show is that if the corruption level is less than a constant and your network is over-parameterized again, but here the sense it needs to be over-parameterized is if the number of parameters is bigger than the number of clusters to the power 4, then what happens is that the labels that the network learns is actually the correct one, not the corrupted one. You feed in the corrupted data, but the label that the network gives you is actually the corrected one. So it kind of like corrects the label automatically. So that's the result. I just want to say that key here is this notion that we discussed, which is accuracy really depends and generalization capability really depends on the distance you travel from initialization. And so what you can show, and oh, by the way, this was with early stopping. So what you can show is that if you stop early, the distance you travel is not too far. Whereas if you want to overfit to the corrupted labels, you must provably travel a large distance. So this is actually a theorem you can prove. So this is why early stopping is successful, because you don't have to travel too far. So that's the intuition. And just to give a very brief idea, I think like I'm almost out of time. Okay, cool. So here is, so let me just go to the main idea, is that if you assume this kind of data clustered model, what happens is that the Jacobian will kind of low rank. If you assume it's approximately clusterable, it will look something like this. So that happens to be that this is kind of the key idea here, which is like essentially during the early phase, the early stopping phase, you're trying to just fit to these large eigenvector portion and ignore this part. And obviously the clusterable model is kind of a crazy assumption because the data may not be that perfectly clustered. But this kind of, let me just go to this last slide. If you look at real data, the Jacobian does have this behavior of kind of having bimodal eigenvalues. So there are some eigenvalues that are very large. Let's say tens of, so the good fraction, but not too large. And then most of it is kind of smaller. So it's a bi-level kind of model. And this is what allows you to prove robustness. So that's the key. I won't talk about that, but I don't even have the slides for that. But this also, in fact, allows you to develop a generalization theory, but this is coming up later. So let me just conclude here. So here I discussed some provable benefits to over-parameterization. The first one has to do with making the optimization easier. And the second one had to do with, it buys you robustness to this corruption phenomena. And I didn't really talk about this, but it also gives you generalization capabilities. So since everybody is advertising for postdoc, I feel like I had to do that too. And I just added, like, this is my location, so yeah. Okay, and so these are the papers, and let me stop there.
So thank you very much. Are there some questions? Yes.
Thank you for the great talk. My question is, by looking at your results, so it suggests basically that gradient descent and SGD will pretty much do the same, right?
Right.
So, but there is this view, like among some researchers, saying that when you run gradient descent, it's going to overfit, but if you use SGD, you will get better generalization properties. So, do you have any comments on this? Because it's basically contradicting.
Right. Do you mean like the concept of flat minima and stuff like that?
Yeah, exactly.
I kind of don't believe that. but I think the issue is that we can never really try because we cannot really try full batch gradient descent, right? So what I can say is that potentially you can get a faster convergence using SGD, right? Because for not in worst case data sets, but for particular data set, doing SGD might, we showed that n passes of SGD is equivalent to one full gradient descent pass. So, but potentially, in a data dependent fashion, like depending on the data, you could actually be even faster, right? So that's the only benefit I see. I'm not sure I fully believe. I can see why there is some advantages to SGD in terms of generalization, because it's like adding some noise. Maybe you come out of some local optima, but I feel like we need more experiments on actual full gradient descent to know that, right? So it's kind of inconclusive.
Thank you.
Another question? Yes.
No, wait for the question is,
yeah, it's recorded.
So actually, in the first paper of this randomness experiments, they also apply randomness to the images. So here, actually, what you're saying is, if you have early stopping, then the random label actually doesn't affect the generalization arrow. But do you think the same results can apply to the case that if you have randomness to the input images?
Oh, you mean completely random? Yeah, no.
Well, like you apply like Gaussian noise, white noise to the images.
Right. I think so our theory kind of may explain that. If the size of the noise is small and you don't add it to all of the data points, again maybe just a fraction, I think inherently there will be some robustness. Obviously, if you kind of tweak the loss, maybe you gain even more robustness. But I think the idea being that over-parameterized models are inherently a little bit robust to whether you corrupt the output or the input.
Okay, thanks.
Okay, another question. Okay.
Thank you. My question concerns the second part on the robustness.
Right.
I didn't get if you had some hypothesis about the regularity of the labels. I mean, the true labels with respect to the original data set, because you would feel that that would be a natural.
Right. So here again, this is under this very restrictive model, right? So really the theory is based on this Jacobian being bimodal, which I showed here, right? That's the theory is based on this. But the kind of theorem I showed is for this clusterable model. So inherently there is a lot of regularity because, if I go back to this statement of the theorem, we're assuming that the input data is kind of very well clustered, right? And multiple clusters can belong to the same class, but it's still very well clustered, right? So in that sense, there is a lot of regularity.
Okay.
But I think what is really at play is like this Jacobian is kind of bimodal, and that's really what's happening. So this is kind of a toy model to have this Jacobian bimodal structure.
Okay, thank you.
Okay, so thank you. We'll stop now. We have the coffee break. We can go on the discussion.